Welcome to Neural Networks 1. My name is Nick Clinton, Earth Engine Developer Relations, and we have...
I'm Gennady Donchyts, Gena.
Gena, cloud engineer, customer engineer.
I'm a cloud geographer.
Cloud geographer extraordinaire, and we're going to be co-presenting today. A couple things before we get started. This is the link. That's the link. That's also the link to this presentation. You're going to want to have that up if you want to follow along. So what we're going to be talking about today is sort of real basic neural networks. Fortunately, we have some machine learning experts in the house if you have more technical questions, and they're going to bail me out if we get in trouble here. But my intention here is to sort of teach you plumbing. And by plumbing, I mean you've got a neural network in TensorFlow, other frameworks coming soon. You want to connect to it from Earth Engine and have an interactive map and that kind of stuff. We're going to show you how to do all that. To make this work, you will need a cloud account. And you will probably need a cloud account with a cloud project with a billing account enabled in order to use some of the features that we're going to be talking about today, specifically cloud storage. If you are a student, I have coupons for cloud credits for you. So if you have to fire up your own project on a Gmail account, for example, and you are fully enrolled in an institution of higher learning, come talk to me. I can give you one of these coupons for $50 credits for your cloud account. So you shouldn't have to pay anything to do the demos. That's the idea. If for some reason you can't set up a billing account, sorry, you're just going to have to follow along or watch your neighbor or something like that. If at any point you get stuck, raise your hand and someone will come and try to get you unstuck, if possible. Does everybody have the link? Good. Okay. For how many people were in one of these sessions last year, just out of curiosity? Okay. So a lot of overlapping content here. The big new thing is that now we have a connector to Vertex AI instead of AI platform. So everything we're going to be showing you today is using this new connector. The old connector will continue to work so long as AI platform is around to accept the prediction requests, but it won't always be. So now is the time to start migrating all your AI-related workflows to Vertex AI. I'm going to trip over that thing at least one time today. This is a blog post that just kind of explains what happened and where to find docs and all that kind of stuff. Okay, I sort of already talked about this, but you're going to have to be registered to use Earth Engine, and you're going to have a cloud project with permissions to enable APIs, set up a billing account, and you might get charges. Again, see me for these coupons. Anything to add here, Gena?
I think in addition to cloud storage bucket, so what this and second training session will use is Vertex AI API. So how many of you actually worked with Vertex AI? Okay, that's very good.
Yeah, excellent. Okay, first things first. This is kind of a weird hybrid of slides and Colab, and I'm going to be flipping back and forth. But you got to get this part set up first. So there is a cloud console, and it should look something like this. So if you go to console.cloud.google.com, you'll see something like this, and you can go to things like cloud storage. And if you see a message on cloud storage that says something like you have to enable billing for cloud storage, then it's going to make you set up that billing account. Evidently, I didn't make a suitable sacrifice to the demo gods. Oh, there we go. All right. So cloud storage, that's sort of a basic setup here. This is, for anybody that's new to cloud and sort of this environment, this cloud console, on the left, you'll find the menu. That's where you get to, the various parts of the cloud platform we're going to be using. Here is your project. So keep track of that project because that's where you're going to be setting up the buckets and so forth. And this is your account on the far right. So make sure that everybody, if you want to follow along, make sure you can get to this point and see cloud storage and so forth. Okay, let's see. All right. As I said, we're going to be going through some demo notebooks. This is the list of all the notebooks. In the first session, this morning session, we're going to be covering these first two examples here. The first one is a notebook. The second one is just a link to a later slide in the deck. Because the AutoML stuff, I want to show you some GUI-driven model development stuff there. The first part of all this is just generating the training data that you need. We'll talk about that in more detail in the second session where we're dealing with larger data sets and you have to use some of these more heavy-duty cloud services in order to generate those data. For the first one, for the first demo, we've already generated the data, and it's the process of generating those data is actually described in our docs. It's the first TensorFlow example on the ML examples page in our docs. It's called TensorFlow from scratch or something like that. And that'll teach you how to generate the training data that we're going to be using, which is just a simple export. And if your data set is relatively small, meaning, let's say 100,000 to maybe 1 million points, export should probably work for you. And that's a fine option. But other options are using the REST API or using a client-based approach, specifically compute pixels. And we've got plenty of docs for that too, if you prefer to generate your training data that way. And then if you've got something really, really large, we'll tell you about data flow and how to use data flow to generate a really large training data set. Okay, first session, this is the requisite neural network diagram that you have to have in every presentation like this. You could ignore most of it. The only point that I'm making here is that a vector is going to come in and a vector is going to come out. And that is suitable for per pixel methods and table methods. And in the afternoon, we'll talk about more complicated stuff. But for now, the important thing to know is just that vector comes in and vector comes out. Ignore the names here. Imagine this is like Sentinel-2 bands or something, and this is like land cover class probabilities or something. What goes in is the pixel vector. What comes out is the class probability vector. Okay. I'm sort of jumping ahead to the punchline here, but this is the new connector. This looks very much like the old from AI platform predictor, except now it's from Vertex AI, and you do get a couple more knobs and parameters in there, but we'll talk about those later. The important thing to note is just that by doing this, you have control over the tile size and the name of the output things, and Earth Engine wants you to tell it what you expect to come out of the model. And so, as I said, we're going to have a vector that comes out. And the other thing to note here is the projection. You want the projection to be the same as, you want the scale and projection to be the same as what you used to generate the training data. The consequences of this is that when you have an image from this thing in the code editor or some other visualization thing and you zoom way out, it's going to ask for all the pixels at that scale that you can see in the window, and that will trigger a lot of requests. So first of all, you're going to get a bill from those requests because it's hosted on Vertex and the model will be predicting stuff. The other thing is when Earth Engine sees a large tile like that, with so many pixels in it, sometimes it will try to cram all those inputs into a single request payload and send that to Vertex for prediction. And sometimes the size of the payload gets too large because you just got too many pixels crammed in there, and you'll get like payload too large error. So beware zooming out when you've set up your model like this for those reasons.
Maybe quick comment. I think these things what Nick is showing, they are relatively early stage released preview kind of mode. And Vertex AI, because not people present here, they don't know what it is probably yet. So it may be worth mentioning that, let's say, the Vertex AI is kind of new AI platform of Google, which much more flexible compared to previous one, where you could basically host any type of models, more as like virtual machines, Docker images. So that's like one thing. And about this scale, you could actually, let's say, disable, put in your code some small piece which would react on a map zoom. And when you zoom out too much, that this code basically won't run. So like prevent some code from running, from fetching tiles when your zoom gets coarser.
Thank you, very important point. This is in public preview right now, which means that hopefully there are no bugs. But if you find one, let us know, please. Okay, this is what we're going for. This is a 3-class model. This is the Bay Area, that's San Francisco on the left. This is a 3-class model. Classes are red, green, and blue. And what do they mean? I'm not sure. I used to call them bare, vegetation, and water, but it's not entirely that. So anyway, very simple classification problem. You'd like to get this map from a neural network running on Vertex AI, and that's what we're going to do.
It's a dynamic world light.
Yeah, the dynamic world, this is like dynamic world extra light, and this afternoon will be like dynamic world light or something. Okay, let's see if I can go to this Colab notebook here. Okay, that's good. How about that? Is that okay? All right. Is anybody who wants to follow along having trouble getting to the notebook? Good. All right, let's see what happens here. I haven't run this thing today, so fingers crossed.
Nick, can you make it bigger?
Yeah. How's that? Is that any better? In the back? Bigger? I don't think we need this. I'll just make it smaller. Can I make it smaller? Yeah. Okay. So, first things first, just run some imports. This is all pretty basic stuff here. You just run some imports. Okay, now we're going to authenticate. And this is going to ask me, am I going to let the notebook use my credentials? And yes, I am Earth Outreach. And I'm going to allow all this stuff. And we should now be authenticated. This is just to cloud. No Earth Engine authentication just yet. Oh, wait, right, just the cloud. OK, now, in this cell, if you are actually following along, you'll have to replace this with your actual project. So for me, it's going to be Earth Outreach. And run it. OK, now, thank you. Now is the Earth Engine authentication part. And we're going to reuse those same credentials. So we've already authenticated to cloud. We should be able to reuse those. There are a couple things that I need to mention here. First of all, you should tell it the project that you want to use when you authenticate to Earth Engine, so that all those Earth Engine calls are being routed through the same project that we're going to use for the Vertex stuff. The other thing is this opt URL. Please point that to the high volume server if you're making any kind of automated requests. The high volume server is a little bit higher latency, but it's designed to handle a much higher volume of requests. So please do include this optional URL when you initialize. OK, what's going to happen? All right. So now we get to the variable definition section, and we have to give it a bucket. And I think I deleted the bucket that I was using yesterday. So I'm going to create a new one. Basically, after running this, I went through everything and deleted everything, all models, all buckets, all everything, to avoid incurring charges to your account. So let's just go ahead and create a new bucket right now. I'll just call it G4G demo, how about? And now choose a regional bucket. Occasionally I've encountered errors that say something like, your data is in a different region from your model or something like that, and Vertex AI will get a little bit pissed about that. So I'm going to choose US Central 1 as the default region, and standard storage, and it's going to say, yeah, this is my personal bucket, so we can enforce public access prevention. And somebody took my bucket name. So let's see. Maybe I took the bucket name for myself. So let's see if I can create another one. G4G demo neural network 1. Let's try that. Region, did somebody take G4G demo just now? All right, well.
You want to select Central?
Oh, did I choose US Central? Oh, no. Sorry, I got to start over here.
Yeah, and maybe while Nick fighting with buckets, the selecting this central region for all resources that you will use, also for like machines, Vertex AI or buckets, it's important because then your model and your data will be collocated basically to each other. If you don't pay attention, you might create buckets somewhere in India, and then your models will run somewhere in Australia. That's not the best way to get high performance platform system. Yep. I think US Central, that's close to where Earth Engine nodes running, if I'm not mistaken.
I don't know.
So it's, I know, so Earth Engine doesn't run multi-region yet. So that's US Central 1 and 2. Okay.
Thank you. Okay, so once you've gotten your bucket, so here's my bucket, and now you're going to enter that bucket name into this output bucket variable. Be sure that this region matches whatever region you specified previously. Let me just explain what the rest of this stuff is. You're going to train a model and save it in that bucket. So that's why you need write access there. You're going to need a container image for the machine that you fire up to make predictions. And that container image has to have all the stuff in it that it needs to make those predictions. So that's what this container image is. Just names for the endpoint you're going to create. The training data, as I say, is already created. And if you want to see how, check the docs. But this is just sitting in this data bucket here, which is EEdocs demos. And that should be public. All of y'all should have access to that. Okay, this is the label we want to predict. It's called land cover. There are 3 classes, red, green, blue. We're going to use Landsat 8 imagery, these bands, to do the predictions. And all this stuff is just sort of some boilerplate that you need in order to read those training data into TensorFlow. Any questions so far? Yes.
Can you just talk briefly about the nature of the training data?
Yeah. Okay, so first of all, you run this thing, and it should find the training and the testing data. Let us know if you have trouble with that. The data are, I think it's about 100 points that are just sort of scattered around in the Bay Area, you know, that map that I showed previously. And these are just points that I labeled by hand and overlaid on a Landsat 8 median composite. And that's it.
I believe there is a link in slide deck or in a Colab notebook to the notebook where this training data is generated. Remember, I saw it somewhere. Like that you will be able to basically reproduce the same, generate the same data set.
It's either in the slides. It must be in the slides.
It should be probably in slides.
Anyway, these data come from that TensorFlow from scratch demo. That's the first on our ML demos page. Okay, you should be able to read the data. You should be able to read the data into a tf.data.dataset. The point of this is not to get anything that's necessarily human readable. The point is to make sure that you can read some data without getting an error. And that's it. Okay, parse the data set. Now, we're starting to get into some slightly funky stuff here. You have to tell TensorFlow what's in there and how it's stored. And specifically, you know what's in there. It's that set of bands from that list, and each band goes to a fixed length feature, specifically a float 32 feature. You have to tell TensorFlow how to parse this stuff out of that file. The way this stuff comes in and out of Earth Engine is as 3-dimensional arrays. So specifically, we want to go from sort of a scalar per band and a scalar per output label to this 3-dimensional 1 by 1 by 1 thing that is like, you can imagine that as just like a single pixel. And because it's 3-dimensional, Earth Engine knows that this thing has a height and a width, which is just 1 in this case. But that's why we're doing this, to put these things into that specific shape so that Earth Engine knows what to do. So specifically, you can run this and you can see that we are getting the shape that we want, and that will enable the model to operate in to make a map out of your predictions. Questions? Good? Okay. All right, the model. I'm embarrassed by the simplicity of this model. Chris, don't laugh. This is like the absolute most simple thing. There might be like even some old-fashioned stuff in here at this point. I'm not sure.
Perfect, Nick.
Thank you. It's perfect for present purposes. And this is just a single hidden layer neural network. I'm sure there are folks in this room who want to do something more fancy. Feel free. But this is just like a real simple network here. And we're gonna wrap it in some pre-processing layers. So specifically, my custom pre-processing layer here just makes it so that you can feed a dictionary of tensors as input instead of a single tensor. I'm saying this badly. If you don't want to feed it a single tensor that has an array of the input bands in it, what you can do is you can wrap it in this pre-processing layer so that you can feed it a dictionary of inputs. And that's nice because then you don't have to convert your images to array images before you send them to the model. So this just lets you use named inputs. And specifically, we just take the name of each band, we take that one by one input, and we stack them all together to make the vector. So we're just doing like 2 array here in code instead of doing it in Earth Engine. OK, now we're going to have a little custom model here. And the model is initialized with your special pre-processing. It might have other stuff in there that you want to do to that data first. And then the simple model that I specified earlier, so that when you run this model, it's going to get these named inputs, stack them all together, feed them to the model, and then give you the predictions back. OK. Questions about any of that? All right. Now, we compile the model and fit it. And this, as I say, is a very simple model. So, it should just crank right along. And, occasionally you get less lucky here in terms of your accuracy. But whatever, this is fine. Anybody have trouble training the model? OK. And then we can just sort of print a summary here, and it doesn't tell us very much because we wrapped it all in this custom thing, but it's a useful check anyway. OK, the way these data come in and out of Earth Engine is as base 64 encoded serialized tensor protos. And the reason for that is, furthermore, it's a dictionary. And so each named band gets flattened into this thing, and then the text is encoded, and that gets sent. And when you get something back, it's in the same format. It's in this base 64 encoded text that you got to sort of unravel again. This boilerplate code here is intended to replace Earth Engine model prepare in the command line. So previously, you were doing Earth Engine model prepare, and this would do the same process. Now we're just doing it here in code, so you don't have to run the command line. And this just returns the same kind of dictionary, where K is the band name here. And then it's, so this is getting the inputs. It decodes the base 64 and parses the tensor out of it. And then when you're done with it, it feeds that to the model. And then when you're done with the model, you do the same thing in reverse. You serialize the tensor, encode it, and send it back to Earth Engine.
So maybe these 2 steps, so what you see here is serialize, deserialize, that's like Vertex AI specific code. So because the data gets sent from Earth Engine for every tile once it will do inference, and then it will encode it properly. And so we need to have this last step to really base, what did you call it? Base 64 protos serialized.
Yeah.
Yes. So it's basically, in other words, this is when data gets sent over a network to the endpoint of your model running in Vertex AI, then you would need to decorate your model with this step so that you encode or decode it properly. And the previous step, it's more to take the dictionary of per band. When you send in data from Earth Engine, it's organized in a way that you have dictionary, and for every key, you get basically band as an array per band. But for TensorFlow or machine learning models, you want to convert it basically to vector form. So there's two steps which are basically decoration, but they are relatively transparent in this new way of working.
Right. So that's why we think this is better, because it is transparent and you can fiddle with it if you want to. We used to call this EEifying, but that's not really correct. It's really more Vertex AI-ifying, because this is the format that Vertex AI wants for your online predictions. And so, we're working on newer and better ways, but they're not ready yet. So for now, you have to do this, and this is just getting things into the right format so that they can be accepted by this online prediction service. Questions about that?
Yes?
As you mentioned that we are wrapping up the model in a container image, right? So can I send a PNG file directly, and the model, whatever the solution is inside that container, deserialize it automatically? I would like to know, is it the limitation of the container, or is it the limitation of the Vertex infrastructure?
Okay, a bunch of questions in there. It's a limitation of the infrastructure. Well, specifically, it's a limitation on the infrastructure as you have configured it in the image that you provide. So, in other words, we're going to provide this saved model artifact, and we're going to provide a container image that knows how to run it. You can create your own custom container image and custom container that does all kinds of fancy stuff, whatever you want. Here we're just using a default container, and the default container is expecting this TensorFlow saved model artifact, and that's how it works. You can have other containers that are running different frameworks that are exchanging data, for example, as JSON payloads. We'll talk about that a little bit later. Under development, though. Okay. I just like to sort of get a visual on what that model looks like. Here you're sending it these named inputs, and then it's getting deserialized, it's going to your model, and then it's reserializing the output. It's also sometimes handy to check the output and or the input, just so you know that the name that it's sending is what you expect. Sometimes, TensorFlow sometimes renames this stuff in a weird way. And so it's important to sort of keep track of the names of the inputs and the outputs. Okay, now we've wrapped the model. So we trained the model. We wrapped it in pre-processing, and then we wrapped it in this serialization and deserialization thing. I am just going to I'm gonna not do this. I don't think I need that. Let's see what happens here.
Can you click the file icon on the left?
What?
Can you click file icon on the left?
File icon on the left.
Yeah, go to left, more left. Yes, this one. And then you can expand. Once model is serialized, and you could refresh on top.
Well, this thing is supposed to be a cloud storage bucket.
Oh, sorry. So it's not locally.
Well, we'll check all this in a second. I might have screwed up the names here. We'll know more soon.
We have it different in different notebooks. So that's.
I've run this thing, I don't know how many times.
It's a preview.
You know, I think that's the leftover test there, which is what confused me here. So it saved the model, and now we should check that it went to the place that I thought it was supposed to go to. And, okay, so there it is. There's a new folder inside the bucket that is storing these model artifacts. And I just have to remember this name. You know, I appended that _test to it. But it's saved in there, and now we should be able to deploy that thing. Yeah, okay, so this test, somehow I forgot to clean out that test from everything, but should be okay. Okay, in the first thing here, did anybody have trouble training the model and saving the model who wanted to do that?
I got a command exception about remove command not supporting file.
Okay, right, all right, so, right, sorry. So basically, I added this command, which I just commented, to remove anything that was already there. And if you run this as is, it might give you like error, I couldn't find that thing. That's okay, because it didn't exist. Then it'll just save it in that same location.
That's TensorFlow thing.
Chris or somebody who is an expert in obscure TensorFlow errors, does anybody want to bail me out here? I don't know.
What's the end of the
TensorFlow compiled the loaded model, but the compiled metrics have yet to be built. Model.compile_metrics will be empty until you train or evaluate the model.
I don't think that, I think it's just saying that member on the model object isn't there yet because you haven't called train. Once you do, it'll update that and then it's available. But I don't think anybody's super excited about model.compile metrics. But if you are, you have to train it first.
Our model's already trained, so we don't need to compile it or train it again. So I've just been ignoring this error, but thank you to whoever asked about what it actually means. Excellent question. Okay. This is the same thing of, you know, deleting the model from Vertex AI. I'm surprised that it didn't give me an error here. Evidently, I forgot to delete that model yesterday. That's okay. It deleted whatever model was there, and now I'm going to upload a new one of the same name. And what is it doing here? You're telling it where you put that stored directory, so it's just pointing to the directory in which you, the one we were looking at a second ago where it had those model artifacts stored. So you're telling it that's where you find the model artifacts. This is the project that you want to send the request through. This is the region. This is that container image that knows how to run the model artifact that you saved. And then it's just giving it some names here.
So essentially what it's doing is you have this container image. It doesn't have model, but it's a base Docker image with all necessary, let's say, components installed, libraries, TensorFlow. And once you pass model to it, you would combine it with that model, and that's how it gets deployed, or that image basically gets uploaded into Vertex AI environment. And I think we can show this in Cloud Console, where
yeah, we will check. Right, so that's a good idea. So now we can check. So specifically, I can go to the menu in the upper left here, and I need
one hint here to search for Vertex AI, because there are many services. You could just go to search bar and search Vertex AI. That's sometimes faster.
There's a search bar?
In the center of the screen on top.
Okay. Anyway, it's here somewhere, and there it is. And so you can scroll down. I want to show you all what's in here, and specifically the model registry. So here's where that thing should have ended up when we uploaded the model to Vertex. And there it is. And now we want to deploy this thing. So to deploy it, we need to first create an endpoint. And we're going to create an endpoint. It's going to have this name. We're already done. Now we just want to discover the ID of this endpoint. You can also get this from the console. So, oh God. It might have just deployed something. Okay, there's the ID. This thing is important because this is how you use, this is all that you need besides the project and the region to connect to this thing from Earth Engine. So specifically, if we go back to Vertex AI here and you click online prediction, I can make this bigger too. And here is that endpoint that we created. And here is that ID that you need. And if you click this, you'll see that we have we're supposed to have a model deployed here. There isn't one, so maybe I'll try to run this again.
So there's some terminology here. We have this model, how it's called, artifacts or images. So when you upload your model, you basically have an image uploaded, but there's nothing deployed yet. And the endpoint, it's basically, this will be the kind of unique URL where your model will be hosted. So that's first step what you do. And then under this endpoint, you would deploy that model using that image which you uploaded before. So it's 3 steps essentially.
Yeah, so the deployment process can take a little while. So let me explain what's going on in the meantime here. First of all, this is where you would specify fancy machines and accelerators if you want your predictions to be faster. So you can specify a particular machine type and the amount of memory you want and how many GPUs you want and all that kind of stuff. If you decide you want GPUs, you can't use that same container image anymore. You got to use the GPU container image so that it has all the drivers that it needs for those GPUs. I think this is also where you would specify number of replicas and some other scaling parameters. If you're running a really big predict job, you might want more than one machine and accelerators on the machines and the whole 9 yards. Okay, once this thing is deployed, we should be able to connect to it from Earth Engine. And let me just run you through the code here. Specifically, this is all just setting up inputs. So, cloud masking function, median composite, and then displaying that input in the map. Here's the path that we're going to use for prediction here. So this is kind of the important part. As I noted, all you really need is the project, the region, and that ID. And that's why, sometimes you lose track of the ID in your code or you want to try a different one or something. Just, you can get that from the console and put it right here and then start making predictions. Here's connecting to it. So you need that path. So Earth Engine knows where to find the model. The tile size is not particularly relevant here because you're doing a pixel-wise classification anyway. You can think of the tile size as like a batch size or something like that. And you may find some performance improvements by getting this to the right size. 1 by 1 is going to be more requests, and 8 by 8 is fewer larger requests. So you might have to just play with that a little bit. Is this readable in the back there? Sort of? Okay. So to get an image, this is all you have to do. And specifically, that Vertex model that you just described in code there, that thing's hosted on Vertex. And now, all you want to do is get some predictions from it. And that is called predict image if you want image outputs. And what you give to it is the image that has the bands that you want and cast to float. This is different from examples that we did previously where first you convert it to an array image and then you send the array. You can still do that, but that was the point of wrapping the model in those pre-processing layers so that you can get a dictionary of inputs and then it'll stack them all together and stuff for you. So it just makes things a wee bit more convenient when it comes time for predictions. The output is still an array. And specifically, it's an array of those class probabilities. And so what you want to do is you want to turn that image in which each pixel stores an array of class probabilities into a 3-band image in which each band stores a single class probability for that particular class. And to do that with Earth Engine, you use array flatten. So array flatten takes a list of lists as its parameter, one list for every dimension. We have one dimension here, so we just need one list in our list of lists. And the one list that we put into our list of lists is the names of the classes that those probabilities represent. What am I missing?
Usually, when I'm not sure if you have link also to the code editor for the same examples, but once you work with inspector, I think here you also will be able to do this with inspector. So when you add these predictions as a layer, it's good to look at this arrays, and then it will be more intuitive what you're actually doing here. That there will be array of arrays.
Right. So yeah, that's a really good point. Often I find debugging in Colab to be more difficult for this stuff. And shout out to GEEmap and its developers. That will probably make a lot of this a lot nicer and slicker. I'm not using GEEmap here, but that is a fine option in terms of getting some more inspector stuff and bells and whistles into your map. I'm not sure if it does the same thing in terms of sending error messages back and forth. So the code editor is pretty good about unpacking error messages from the response that it gets from AI platform and telling you what it is. And often I find those errors are quite useful for debugging this stuff. So typically I will have both JavaScript and Python version to do this prediction. In the afternoon session, I show you a way to just inject the project and the endpoint ID right into a JavaScript so that you can do all this in the code editor. Here I just, we're doing it in this notebook. And it is still deploying this model. This can take, 20 minutes to half an hour, depending. So, in the interest of time, we're going to probably move on here unless this thing finishes very soon. But suffice it to say that this is what it would look like if once the model is deployed and you connect to it, you're going to get a map of probability per pixel. So specifically, the very red pixels, the probabilities are set to red, green, and blue. So a very red pixel means that the class probability for red class is quite high and the class probabilities for the other classes are quite low. and same thing on the blue. High probability of blue class, and in the vegetation, high probability of green class. Questions about this while we're waiting for this thing to finish? Where did it go? Still deploying. Questions? Yes?
In the last version, where you used the Google AI platform, there's a step about EEification the model. I'm wondering where does it go in this new version, or is it not needed anymore?
Yeah. So first of all, we're renaming that. It's not EEifying anymore. It's Vertex AIifying. And that happens specifically in this section, which is called deserialization. And so now we're just doing that step in code instead of EE model prepare. Other questions in the back?
Which part of this workflow is actually costing money in terms of resources?
Great question. Let's see. I'm not sure. Deploying the model for sure. Okay. Once you've deployed a model, that machine is sitting there waiting for you to make predictions. And unless you turn it off, you will get a bill, whether it's making predictions or not. So just having an idle machine for a deployed model is going to generate a bill. You also get billed for predictions. Is that true?
I would check. I'm not 100% sure. I'm not sure if we have expert from Vertex AI. No. I'm looking at Googlers. But
I think if the container is already running, it doesn't matter if it's a prediction or not.
Right, okay.
yeah,
so
but maybe one comment there is like to really be aware of to understand, let's say, how large these expenses could be. It's worth also checking something called pricing calculator in Google Cloud. That's where you can select, for example, imagine I would have this amount of storage, or I would go to Vertex AI and select this specific machine with that GPU, or in different regions also. So the prices really might vary from region to region. So it's good to understand, let's say, what the expected costs are. And you can always, if you do these test models, it will not generate, let's say, large costs. So it's after doing these predictions, just checking your billing, or then looking at how large costs, where they are coming from, then you would have understanding really of what actually costs money in these steps.
Right, so I think the short answer is we're not sure. I think what this gentleman said might be true, which is that if the machine is up, you're paying for it, whether it's making predictions or not. You might pay something for cloud storage, depending on how much stuff you have stored in there. There's a freemium tier there, but I'm not sure entirely where it is. If you are a commercial and or operational user of Earth Engine, you can also get billed for the Earth Engine requests. In other words, we have to generate the composite and then send those pixels to Vertex and then get the predictions back and show you them. And all that stuff is billable for Earth Engine. I ran this demo. I ran all the day's demos on an external account the other day and then carefully shut everything down, and it cost $25. But this is like real, simple stuff. You leave that machine on or you do a big export, the bill could be a lot higher. Again, if you're a student and you need some help covering that, let me know. I have some coupons for cloud credits.
For one GPU, NVIDIA Tesla V100, it costs only $2.8 per hour, just for one GPU.
Okay. Is that a good deal? I'm not sure. I mean, there are pricing pages. If the question is explain cloud pricing, I will not be able to answer that. It's so complicated. Gena might know more. Yeah. So the advice, I think, from Brady's talk, I think it was. Is Brady in here?
Nope.
Anyway, Brady gave a talk yesterday about sort of cloud theory, and he was suggesting to run something small first, and then monitor it. Monitor it using metrics and the Cloud Console, see how much it costs, and then start to scale up so you don't get a surprise. Okay, so fingers crossed. Here's our input data. And at some point, if I've done everything correctly, we should start seeing predictions here. Okay, good. So we're getting our predictions tile by tile. I'm not sure how good they are because we got a little bit unlucky on the training of that model, but that's how the plumbing works. Anyway.
Zoom in.
Zoom in. Gena wants me to zoom in. I don't know what's going to happen. Yes, sir.
So I have like two questions. One is when you are deploying this, is there a way you could say like shut down after 1 hour kind of thing when you are deploying from AI?
That's a good question. Whether you can sort of automatically turn off the machine after a certain amount of time or something like that, I don't know.
Yeah, basically you could, because now we're doing this from notebook, but all the steps of deploying, so Nick did some steps like creating buckets manually, but all the steps, it's something what you can automate, and when you're doing prediction, you can basically script, even like with, we have something like Terraform-based scripts what you could write. It's really to spin off, deploy models, do prediction, export, and then turn down everything or delete buckets. So that's at the end when you go into production or want to scale, then it's worth like automating all these steps in a separate script instead of doing this manually.
We should be able to watch some of this happening. So, whoops. Was that the one I wanted? No.
Go to online predictions.
I thought we were going to get some graph. There we go. All right, so there are our predictions, that stuff. And we should be able to look at Earth Engine and see the same thing. It might just I think it gives you some charts here. Right, so it's going to sort of tell you where, what APIs are running and the requests that you're making and all that kind of stuff. This is quite handy because you can't necessarily do this if you're running an export, but if you're, well, that's not true. If you're running an export, you should be able to see this same kind of graph, but you can see it in real time here where you're scrolling around the map and it's making predictions and it's appearing here and you can check what the errors are and the latency and all that kind of stuff. So the console is your friend for this kind of monitoring. Questions about any of that?
There is a step in which you fit the model with 13 epochs.
Yeah.
That is happening where? In Colab.
That happens in Colab. And we can get away with that because it's a pretty small data set and it's a pretty simple model. In the afternoon session, we'll show you how to do a bigger, more complicated model and train it on Vertex AI. Other questions?
Sorry, the second question. So when you are deploying this way, is it auto-scaling or is there an option you can turn on and off the auto-scaling?
I believe it's auto-scaling to 1 right now. And you have to tell it if you want more than that. So yes, in the deployment, you would tell it, how many nodes you want and, all that kind of stuff.
Can you run more than one model with the same instance? Say, don't that have a lot of prediction when you have a bunch of models that you want to serve up?
What do you mean the same instance?
Whatever unit it is we're paying for when it's deployed.
I think the question is, can you deploy more than one model at once? And there are multiple answers there. You can certainly do that. You can deploy as many models as you want, but then Vertex AI is going to ask you to choose how much traffic goes to each model. And the reason for that is that then you can sort of phase one in and phase another one out, by changing those percentages. I think what you're asking is, can you have like a bunch of models? And I think the answer would be yes. You would wrap those the same way and then return a dictionary of outputs where, the keys are the model names and the results are the model values, and you just have to plumb all that through those pre-processing and custom model code blocks. Okay. Table predictions. So you can do the same kind of thing on the properties that are stored in the rows of a table instead of in the pixels of an image. So if you've got that same set of bands in the features of a feature collection, then you can call model.predict properties. So before we had predict image, now we're doing predict properties. And there is some funkiness here, which is that I got pretty lazy when I was building this demo. Specifically, I didn't want to train another model. I just wanted to use the same model, for table stuff for the demonstration. So that's what this funkiness is. This is making that 3D array that that the model expects in each feature. So normally you just have a feature with a number in it. And that's not what the model wants. It wants this 3D array thing. And so you turn each of your features into this 3D array thing. And then, fingers crossed, we should be able to just connect to this sucker. So here's our input properties. So these are these kind of weird little arrays in here. And here is the output. And somewhere in here we should have predictions. Maybe they're at the end. OK, there it is. So there's your probabilities that come out the other end. And so you just have another table that stores the output predictions in a new property.
How cool is that?
How cool is that? Questions about table models and predict properties?
Sort of higher up, when we're connected under the section that says connect to the hosted model from Earth Engine, where we display the imagery.
Mm-hmm.
When we're defining the mass LASR function, we're multiplying certain bands by constants and adding other constants. Could you explain a little bit what that's about?
Yeah. So the surface reflectance data comes as scaled reflectance or something like that. And this is just applying the scale factors and offsets that you need to get it into actual surface reflectance between 0 and 1. And all this stuff is just straight out of the code editor examples. Is Justin Broughton in the house here? I think he wrote this example. Thank you very much, Justin. And so I just copy it straight out of there and convert it to Python. Yeah. So the question is, why aren't you adhering to Google style guidelines in these demos? And
It's a preview.
the answer is yes. There is a style guide, and you can find that on GitHub. And again, I plead laziness. And this thing was made by copying and pasting a bunch of stuff from all over everywhere, and it should not be named this way. We have very specific guidelines for both Python and JavaScript, and I'm being pretty sloppy here. But thank you for the question. Yeah, I mean I'm sure there are coding experts in here who can sort of provide some more details, but generally I capitalize global variables. So if it's meant to be used in more than one cell kind of thing, it's capitalized. And it's a little bit funky here because methods inside the Earth Engine API are camel case, but Python is snake case. What's the
Underscores.
Yeah, underscores, snake case. And so I'm being like pretty sloppy here about here's the I'm trying to do that, but I'm not always succeeding. Okay, how are we doing on time? We have 8 minutes left. The other thing that I wanted to show you here is, okay, so we talked about tables. You set up the model in the same kind of way, specify the input properties and the output properties, and the dimensions that it's expected to be, and then you do table model.predict properties. There is a slightly fancier, well, it's much fancier actually, a much fancier thing called AutoML. And the way AutoML works is that there are a bunch of modes. So you can have like image modes that include segmentation or classification or object detection. There are table models that can be regression or classification. There are sequence models. There's all kinds of fancy stuff. And what it does, in this example, we just take a data file, a CSV file stored in cloud storage. AutoML is this black box here. We don't really know what it's doing. But it can be deployed, and then you can get predictions. The nuance here is that your predictions come and go as JSON payloads. That is a feature that's under development. So the example here is, object-based crop classification. This is, a variant of some example we've got sitting somewhere or other. You want to classify the crop type in a field, and there are emergent properties that include the height, width, area, perimeter length, spectral mean and standard deviation inside these objects that might be quite useful for a classifier that is trying to determine crop type. So build up a data set and make an AutoML table out of it. Here's how you do that. There's this data set that I just generated here, and you can see that script if you want to know more. But this thing is just sitting there in cloud storage in a public bucket. And we should be able to make a table out of this thing. So if we go back to Vertex AI and we go to datasets, you can create a dataset. And we'll just call it G4G demo foo. And so here are all the different, fancy things that you get here. This is why I really wanted to show you guys this, because like there's a lot of fancy stuff in here, and we want you to have access to that. We do have to tinker a bit with how that connector works, but there's a bunch of stuff here. And for example, we can choose a table and create this a regression classification table here, and then it's going to ask us, well, where do you get the source files? And that's where I can just copy this. Whoops, wrong link. It's this thing here, and that is a real typo, meaning that this is a misspelling, but it's a misspelling in the actual file. So. Sorry. So that's how you start this thing. And then you click Generate Statistics. This is why I find this thing kind of handy, because you can generate statistics for your tables, and you can sort of really quickly see whether one of your features is wacky or anything like that, how many missing values there are, how many distinct values there are, and finally, you can train a model on this. So you would do other, and then, it's a classification, AutoML, and now it's going to ask you which column you want to use. So it's going to be crop index, and you say yes, no. These are the features that you want. This is our target variable, so it's not going to use that. And, do I have to transform? Oh, continue. And now is the fun part. The fun part is, how much do you want to spend? And usually I get pretty cheap at this point, and I'm like, an hour is the minimum that you can spend. So let's try it for an hour and see how it goes. But if you've got some big fancy model, you can train it for as long as you want. And once that is done, you can connect. You do the same thing. You'll have a trained model that you can find in the model registry. You can deploy it to an endpoint, and then you can connect to that endpoint from Earth Engine. And the way it works is, so you get all this stuff. This is just showing you all the fancy stuff that you get. You get all fun charts and graphs and accuracy of your trained model. Feature importance rankings, confusion matrix. You deploy it, and this is how you connect to it. The punchline is, you can't do this yet. It's in development, but it's coming soon. Oh, crap, I wasn't supposed to say that. But it's in development, and so we're excited for you folks to be able to use all those features too. We have 1 minute left, so I'm going to wrap it up. We have time for like 1 or 2 questions, I think, if there are any. If not, we will see you back here in Neural Networks 2 at 1:30.
One question.
Oh. Right, thank you. Thank you very much. Close it all down, delete every model, undeploy the models from your endpoints, delete your endpoints, delete your buckets, delete your data sets, clean it all up.
Usually safe way to do these things is create new project. When you do experiments, create buckets, spin-off machines, then just delete the whole project.
Right, you can make a project and delete the whole project if you want.
Yes, too late. Sorry for that, yeah.
Okay, thank you very much. We'll see you in part 2 in the afternoon, perhaps.